Today's first talk is by Marc Levine on quadratic Welschinger invariants.
Thank you, Dan. I want to thank all the organizers of this workshop and for inviting me, and also the organizers of the overall program. It's been here not so long, just a week ahead of time, but it's been a real pleasure and very stimulating environment. And so thank you all. And thank you all for coming this early in the morning. So what's this about? Well, let's see. The idea is to use some aspects of A1 homotopy theory to construct a nice theory of what you might call quadratic refinements of numerical invariants arising from enumerative geometry. So as maybe a first example, so this is a way of background or framework for what I'm going to tell you. So the idea is you take integral valued invariants, intersection numbers, just counting things, and replace them with invariants living in the Grothendieck-Witt ring of quadratic forms over your field. So what is this? This is equal to, you take non-degenerate quadratic forms or symmetric bilinear forms. I'm going to stay away. We stay away from, in this talk, characteristic 2 and 3 even. So don't go near there. Non-degenerate quadratic forms, mod isometry or isomorphism. Then you take this thing, this has a monoid structure, you take the group completion, and that's what that is. It has a ring structure given by some kind of tensor product of forms. Okay? And there's also allied to this a quotient, the Witt ring, and this is equal to GW of k modulo the ideal generated by the hyperbolic form Okay. So the idea is instead of intersection numbers, you want to get some kind of numbers viewed as quadratic forms here. And why would you want to do that? Let me give you an example. The typical numerical invariant. So if you have x, say, smooth variety over the reals, then there's, in this theory, there's a Euler characteristic. In fact, there's just over an arbitrary field, let's say characteristic 0, or if it's smooth and projective over an arbitrary field, this lives in the Grothendieck-Witt ring of R. And there are two natural maps here, one going the rank map, going to the integers, which is the same as the Grothendieck-Witt ring of C. And then there's another map, a signature map, also going to the integers. And what does that do to this thing? This thing sends it to the Euler, topological Euler characteristic of the C points with the analytic topology. And under here, this goes to the topological Euler characteristic of the R points, again with the analytic topology. So that's sort of the typical pattern, at least for things that admit an embedding into R, that these quadratic invariants in enumerative problems should tell you something about the classical problem when you take the rank, and when you take the signature with respect to a real embedding, it should tell you something about the problem over the reals. So we want to pursue that theme. What happens over an arbitrary field is at present a bit mysterious. I should say, so Jesse Cass and Kirsten Wickelgren have a nice one nice result that gives them congruences. If you take this counting problem for lines on a cubic surface and you do it, you get a quadratic form, and if you look at it over a finite field, it gives you congruences telling you something about the different types of lines, their fields of definition, and local behavior around the line. Mod 2 congruences. Okay, we won't talk about that here, but let me tell you what today's problem is. Counting rational curves. So this is, in some sense, the baby problem that gave birth to Gromov-Witten theory in the classical case when you're just counting these types of things. So what's the curve counting problem? On surfaces. Let's just say on surfaces. In fact, on P2. So of degree D in the plane. Make it nice and simple. Okay. So what's the basic, the geometric problem? Let's say we work over a field K algebraically closed, and if you like, even C. It's just more or less the same story. Okay, so you consider curves of degree D in P2. And this is a set, but it naturally forms a projective space of dimension, what is it? D plus 1, D plus 2, over 2 minus 1. And there's probably a better way to write that. And inside here, you can take a collection of points. So there are two kinds of conditions you can impose on two natural or obvious conditions. Condition 1 asks the curve to pass through a given point. Condition 2 asks the curve to have a node, so an ordinary double point somewhere, but you don't care where. Each of those conditions are one condition. And so, on the other hand, every time you ask the curve to acquire a node, the geometric genus, in other words, the genus of the smooth model of the curve drops by 1. And since a curve of degree D has genus D minus 1, D minus 2 over 2, asking for the curve to be rational is exactly those many conditions. So what you can do, you can look at a subspace in here of codimension equal to that number, and on that subspace you'd expect to find finitely many rational curves. And how do you find a subspace of that codimension, of that dimension rather? Well, the codimension is then 3D minus 1, so you ask for the curve to pass through 3D minus 1 points. So inside of here, you have curves degree D containing D minus 1, 3D minus 1 points. And inside here, you expect to find finitely many rational curves. And that will be the case if the points are in general position, which, if you're thinking over C, just means outside, well, it's outside some algebraic set parametrizing the points. So if you want to think in classical terms outside of a set of measure 0, that will be the case. You get finitely many, and you let ND equal the number of this set. Okay, so there are nice formulas for these NDs, at least recursive formulas. So I think the nicest ones, I mean, there are various. There's Kontsevich, Amaraso, Harris, Bolton, Ponde. Various, lots of names. Look at this. Let me just mention the form. There's a funny form, just so you see that you get a formula. This ND has a recursive formula. The sum overall D1 plus D2 equals D. Both DI is positive. And then you have some funny thing, I'll probably get this wrong, N1, ND1, ND2 times D1 squared, D2 squared, 3, maybe it's, I have to look. Oh, I have to look somewhere else. Not that it's going to play a role at all for our talk today, but just so you see something concrete on the board. Where is it? something like, let's see, I can remember 5, 3, 7 times 2. Yeah, here's a, I think there's a 1 minus 1 here, and I think there's a 3D minus, let's see, what is it, 2D? Something. Oh, I forgot it. Wait a second. I'll have it. Just a minute. 3D minus 4. Oh, that's where it is. And then minus D1 cubed D2 3D minus 4. And this is a 2. This is 1. There we go. So there's a recursive formula. Just to give you a list, this is 1, and 2 is 1, and 3 is 12, and 4 is 620. And I didn't figure out exactly what N5 was, but it's more or less some huge number. Yeah, more or less 10,000. And 6 is roughly 1,000,000. So, yeah, anyways. But this fits into Gromov-Witten theory in that it's telling you some quantum intersection product is associative. That's where this intersection formula comes from. Okay, good. Not so important for us. So, we're interested in the story over the reals. That's where our story begins. Okay, so over R. So what can you do? Well, you start out with a real configuration of points. So what does that mean? You start out with, say, points P1 to PS in P2 with real coefficients, and then you have conjugate pairs. So this whole sum, let's just, the sum of the PIs plus the sum of the QIs plus the QI bars is conjugation invariant. So you can expect to find some real solutions to this problem. So then the question is, how many real rational curves of degree D contain the P's, Pi, Qj, Qj bar. Now, here, this is actually an intersection problem. If you take these points in general position, so you get a finite answer, and if all the intersection multiplicities are 1, that's an open condition in the parameter space for these number of points in P2, and that's a connected topological space, so the number is constant. Doesn't really matter which points you choose. But here, the parameter space is in the reals, and the complement is algebraic codimension 1, so real codimension 1, so you have walls in the problem. And here you actually get the answer depends on the choice of points. So there's a wall crossing phenomena. So in other words, you take some point, and maybe it's not in general position, but you can always move it a little bit so it's in general position. You'll get some number, and then you move it to some other collection and move it so it's in general position. You might get a different number. It's not just one number. So as usually what happens in real intersections, you have to assign signs. So that's the Welschinger assign to each such curve. So So let me tell you how he does this. So you have a curve C, and it has a bunch of singular points. So here's a singular point, and let's say it's a real singular point. X, it's a real singular point. Here's x prime, another real singular point. And then nearby the singular point, it's supposed to be an ordinary double point, so the local defining equation is a non-degenerate quadratic, and there are two possibilities over R. It either looks like this or it looks like this, right? This is something where in local coordinates it looks like, say, T1, T2 plus higher order terms equals 0. And here it looks like something like T1 squared plus T2 squared plus higher order terms, or minus that, it doesn't matter, equals 0. And so he gives a sign. This one he gives a +1, and this one he gives a -1. And then over C, you define the mass of C. The Welschinger mass is the product over all the real singular points of these signs. Okay? And then the theorem is, let's see, well, I'll write over here. Theorem, this is Welschinger's theorem, that if you take the sum of these Welschinger masses for C passing through the PI's, QJ's, QJ bars, and it's in general position. In other words, outside some algebraic set, C rational, then this thing is a number which just depends on the real type of the points. In other words, how many of them are real and how many complex conjugate pairs you have. Okay, so that's the theorem. And so what we want to do today is, so today we want to refine these two results. Well, we're not going to give a, I mean, this count is whatever it is. They're also, I mean, he doesn't count what this number is. He doesn't tell us what this number is, but subsequent works give formulas for this thing, which I'm not going to talk about today. But so today, what we want to do, or the goal, is to find this number, this pair, NDWRD, to a quadratic form so it's a valid descent over an arbitrary field. Okay, so and that's a rough goal. So what does it mean that I want to find a quadratic form? Let's call it vel D, such that when I evaluate it on the suitable parameter space, if I take vel D of, you know, this P dot plus Q dot plus Q dot bar at this point, then I take the rank, will give me this ND, and the signature from over R will give me this WRS. But actually I won't get this. It turns out that he made the wrong choice of point of signs, so there's actually a correction factor by something which just depends on the degree. So that's what we'll get. And
are you saying well D doesn't depend on R and S?
This well D depends on something. But it's constant over, so the theorem is that this well D is constant over A1 connected components in an appropriate parameter space. So I'll have to say more about that. Yeah. So, and the fact is that over R, the connected components of the parameter space are determined just by R and S. Yeah. So it completely recovers his invariance result and says more over an arbitrary field. Okay, so that's the goal. Let me say how you set this up. Any questions? Yeah.
So you've got well D of a thing. Is there a divisor? Is that what?
Yeah, I'll say what it's a point in the parameter space. I'll have to say what the parameter space is. The parameter space will be 0 cycles of a certain type on P2. That's the parameter space. Yeah, so these are points in P2, not a divisor, right? So they're of course a divisor on the curve on which they lie, but that you don't know the curve in the beginning. You start out with the point with the sum of points on P2, and that'll be our parameter space, some open subscheme in a symmetric power of P2. Any other questions? Okay. So let's see, the first thing I want to do okay, so let me say what's the parameter space. So here's the quadratic version. First, the parameter space well, we start out with sim 3D minus 1 of P2. So what does this mean? Well, I mean, this is just, as a scheme, this is just P2 to the 3D minus 1 modulo the symmetric group. Okay, but what does it parameterize? Parameterizes zero cycles. Well, more or less. I mean, in positive characteristics, it's not quite right, but it won't matter for the story later on. Anyways, characteristic 0 certainly parameterizes zero cycles on P2 of degree 3D minus 1. So we should fix a field that we're working over. So what is this? So this is over K. So what does this mean, degree over K? Well, if you have a point P in P2, a closed point, I mean, you can think of it as it's some affine space in some A2, so it corresponds to some maximal ideal in a polynomial ring in two variables. And the quotient of the ring modulo at maximal ideal is a field, which will be a finite field extension of K, that's the degree. So then you have the residue field, that's this quotient ring, and this thing here is the degree over K of P. And so a zero cycle is a sum, so maybe I should say effective. So what's an effective zero cycle? It's a sum of such points. And this has a degree. It's just the sum of the ni's, the degree of the pi's. So that's the degree over K of this thing. So it just parameterizes sums like this, where the ni's are all non-negative, and the degree adds up to this 3D minus 1. So inside this symmetric product, we have our parameter space. This is an open subscheme inside here. And what is this? Well, So first of all, I can write it as a quotient. You take P2 to the 3D minus 1 minus all diagonals. Okay, so just the product is just all tuples of points in P2, 3D minus 1 points. This parameterizes distinct points, and now you mod out by the symmetric group. And so, roughly speaking, this parameterizes sums of distinct points. And what this really parameterizes, this parameterizes effective zero cycles of degree 3D minus 1 over k of the form, let's call it zero cycle A, sum of pi, say 1 to m, where p1 up to pm are distinct, and geometrically, so each of these points, when you pass to the algebraic closure, it splits up into its sum of conjugates. And you want that sum to be also distinct, which just means it's a separable field extension. Okay, so that's what, over a characteristic zero field, that's no condition. Okay, so that's what this is parameterizing. And this will be our parameter space for the conditions that a curve passed through 3D minus 1 points, but over some non-algebraically closed field. Okay? So that's our parameter space. What does it look like over R? Well, over R you have two kinds of closed points. You have the ones with residue field R, those are the R rational points, and then you have the ones with residue field C, and if you view that over the complex numbers, a closed point with residue field C splits up into two distinct conjugate points. And so, and that degree is exactly saying that the total degree over C is 3D minus 1. So we're getting back to the picture of, excuse me, of a real configuration of points. Okay, good. So now, inside of here we have a nice locus, or the generic locus. So what's the generic locus? So this is our parameter space for our problem. This is, and the answer at the end will be, I'll have a section of the sheaf of quadratic forms of the Grothendieck-Witt ring over this space, and which, when I evaluate it at a point in general position, will give me my quadratic invariant, which I haven't defined yet. So what's the good locus in here where I can actually make geometric sense out of things? Inside of this guy, let me just put a little delta. This sits inside of here. I have this parameterizes, let's say, the set of points A, sum of pi of this form, 1 to m, such that there are finitely many rational curves C in the plane containing all the pi, all such C are irreducible, so geometrically, if you like, geometrically integral. So again, when I look at it over an algebraically closed field, it's not a square, it's not two conics together, it's just a quartic curve. right? That's the difference. Geometrically integral and has only ordinary double points, so nodes, as singularities. So that's the locus on which I can define my invariant directly. So let's take such a C. Inside of P2. Let's say it's defined by some equation, and when the equation has coefficients in a field big K over my base field little k, we say the curve is defined over big K. So we'll just say defined over some field K containing little k. We define its mass and this will live in the Grothendieck-Witt ring of the field of definition K as follows. Okay. So this is where we have to make the quadratic refinement of Welschinger's plus minus 1. And the point is that plus minus 1, well, is just what a number is modulo a square in the reals, right? It's either plus 1 or minus 1. So that suggests you're looking at a one-dimensional quadratic form, right? A quadratic form of the form x goes to a unit u times x squared, and then up to change of coordinates, the u is a unit, and it's only determined modulo squares. So you want to define a one-dimensional quadratic form which replaces that. So first of all, let's take z in C a singular point. Okay, so here's our singular point. Here it's going to be an ordinary double point. It looks locally, C looks like this. We take local coordinates, say x1, x2 on P2 at Z. So they vanish. In other words, these are things which, in the maximal ideal, things which vanish at Z, and they give the local parameters to P2 at C. And we take a local defining equation for C near Z. I mean, C is defined by a single homogeneous polynomial of degree D, and one way you can get such a local defining equation, let me call it F. You could take the global homogeneous form defining C and divide by the dth power of a linear form that doesn't pass through Z. That's one way to get such a thing, but there are lots of ways to do it. It's not unique in any case. But what we can do is we can form the, what's it called, matrix. Oh dear, oh dear. My father said the knees are not the first thing to go. So, let's see. So the Hessian matrix, right? And then its determinant. Okay? And this will be an element. So the curve is defined over K. The singular point is going to be, I have a residue field, some finite extension of K. The residue field, let's call it KZ. So this will be in KZ. And it'll be a unit because it's an ordinary double point. That's the condition. And we're outside of characteristic 2. So just take this determinant. We note the following. This Hessian determinant is well defined. So I made two choices, and it's independent of the choices modulo squares. Well, why? I mean, if I change F, I can change F by a local unit. Okay? But then I'm evaluating at Z, and since the point is a singular point, the first derivatives of F vanish, And that means the second derivative of f just get multiplied by the value of the unit at z. But it's a 2 by 2 matrix, and when I take the determinant, then that comes out as a square. So that's the first choice, doesn't depend on the choice of f. And if I change coordinates, well, this thing changes at z by, like a quadratic form. So if I have the Jacobian matrix of the change of coordinates evaluated at z, call that A, this will change by A transpose, and the determinant will change by the square of the determinant of A, so it doesn't change. Okay, so that's that. Good. And now, well, I have all these points. I want to get back down to k. For each point, I can take the norm of this unit down to k. This is a finite extension of k. And then take the product over all z. So I take the product over all z in the singular locus. And then I take the norm from kz down to k of this Hessian determinant. Okay, that gives me a number in k defined mod squares, and then I take this bracket means I take the associated rank 1 quadratic form with this number as the unit. So if this is u, this is the quadratic form, x goes to ux squared. And I take its class in the Grothendieck-Witt ring of k, and that's equal to this mass. Okay, now over the reals, again, there are only two possibilities here, more or less. It's either x times y or x squared plus y squared. In the x times y case, then you get a minus 1 here. In the x squared plus y squared case, you get a plus 4. So over the reals, you get exactly the opposite of what Welschinger chose, and the fact that the complex points there are always an even number of them, and there's a total of d minus 1, d minus 2 over 2 points means that this thing is just off by that factor, just depending on d. Okay, so this is more or less, this thing will be then equal to, minus 1, d minus 1, d minus 2 over 2 times the mass of c for k equals r. Okay, good. So that's our mass. And then I need to define a second parameter space, which is really where the counting is going on, in order to define the global invariant. Okay, any questions so far?
Would characteristic 3 have mapped it yet?
Not yet. No, it comes in because you have to do some kind of, if I have time, I'll get to that. So, hold on to that question for just a minute. I'll come to it. And in fact, probably characteristic 2 doesn't matter either at this point. I mean, if you use symmetric bilinear forms instead of quadratic forms, you could probably get by in characteristic 2, I guess. I didn't think about it too much because there's so much going on at the prime 2 with everything that, right? At every stage, prime 2 has to be avoided. So it's not just definite, but this mass you could certainly define in characteristic 2. Okay. So, well, I mean, I think I can define the invariant now. So if you take a point A, sum of pi 1 to m in this good part of the parameter space. No, never mind. Nope, still need to do something, sorry. Good. So now we need a parameter space for, not for the base loci, but for our curves. Okay. The problem is, I want to say exactly what this field K is. I want to get the right choice for the field of definition of my curve. So how do I do that? Well, there I have to use this construction of moduli space of stable maps, or moduli stack of stable maps. Stable maps of genus 0, 3D minus 1 pointed curves to P2 in the curve class let's say D times a line. Okay, so whatever this thing is. So I mean, roughly speaking, this so a stable map, such a genus 0 curve, it's something, well, you have to say what this is in families. I'm not going to do that, but a geometric point of this thing would be a tree of rational curves, right? So they're just connected at single points, together with a map of that into P2, so that when you pull back a line back to this tree of rational curves, you get something of degree D. And it has to also be endowed with 3D minus 1 distinct points. And it has to be stable, which means that the automorphism group of that structure is finite, roughly speaking. And then you make this into a functor, and you defines the Lean-Mumford stack, and blah, blah, blah. I don't care. So, but that's not what we want, because this is a tuple of points, and I don't have a tuple of points, I have a sum of points. So you mod out, you take the quotient stack, you take this, put a little sigma here. So for those of you who don't like stacks, I mean, there are probably lots of you here that love stacks. I'm not a big, I don't like working with stacks when I can avoid it. And the nice thing is that all the things that arise in this problem are inside the scheme locus of this stack. So it's really just a scheme. It's just a smooth scheme. Smooth quasi-projective scheme. Well, I mean, it doesn't get much, I mean, what more? I mean, it's okay, it's not an affine space. I mean, can't do better than that. So this thing is this, you just take this modulo the symmetric group acting of this guy by permuting the points around. And just as taking P2 modulo the symmetric group, so this thing, of course, will map to, the points are distinct, right? So this thing will map to this sim 3D minus 1 of P2, 0. There's a map here, pi, by just sending, so what's this, no, sorry. It'll map to here by doing what? What's this map pi? So a typical thing in here, you take some x in this guy here. So what's x? It's a genus 0 curve P together with a map from P to P2. Gives you a curve of degree D, if you count things with the right multiplicities, together with a reduced zero cycle. Now it's a sum of points. The PI are distinct, let's just call them separable points on P, minus the singular locus. That's what that is. Okay, and now you associate, what does pi do to this? Goes to pi of x, which is you just apply f to a. Okay, now these may no longer be distinct, so you don't land in this open guy, but we want to land in the open guy, so we just, restrict. Okay, so yeah, but let me, inside of here, of course, we had this sim 3D minus 1 of our really good curves. Okay, here we have pi. Let me just call that this thing here. Instead of putting all the, here we have my sim 3D minus 1, p2, 0. And then, of course, we just, p2d. Then we have the various inverse images. Okay, good. Just take the inverse images, right? So all the things in here are the ones where all the curves, all the rational curves that pass through these points are geometrically irreducible and have only nodes. So that's what we're getting here. Each of the x's here looks like this. X is a p, which is over an algebraically closed field, is a p1. It might be a conic over my given field, but it's a smooth rational curve. We have f from p to p2. We have a zero cycle A, and the property is that f of p, which is c, has only ordinary double points. It's geometrically irreducible, and f of A is now, let's say, a sum pi, 1 to m, distinct points. Distinct separable points. And this thing is my pi of x. Okay. So now I can define my global invariant. But only on this open subset. Okay, so for such an x over here, I define right. So now let's take y in this sim 3D minus 1, 2, 0 delta, and then pi inverse of y will be x1 x r. Oh, I should mention, I won't have time to prove this, but this map is finite and a tau. So this is just a covering space, as good as you could possibly hope for. And the proof is quite easy. It's some elementary local deformation theory for curves, maps of curves. It doesn't get the most elementary deformation theory you could ask for. So you have these R points. And now what I can do is I can, for each of these R points, I can now take, so xi is pi fi from pi to p2, and a collection of points with the property that fi alpha I is exactly this y, and I can define ci to be fi of pi. This is inside of p2. This is a nice rational curve with ordinary double points, And I have, this thing has a field of definition lying over the field of definition here. So I can take k of y adjoint xi to be ki. This will be, this curve, ci, will be defined over this field. And then I can associate to this thing its mass. So I define this Welschinger invariant at y to be the sum I equals 1 to r of these. I want to take these masses of these ci's over these fields ki, but that's not in ki, but this thing over ky is a finite extension, and it's a separable extension. So I just take the trace as quadratic form from ki down to k of y. And this will live in the Grothendieck-Witt ring of the residue field of y. So I can do that for every y. And it's not hard to show. So an easy lemma. It's essentially because as you move around on the moduli space, in the place where the images of the curves are ordinary double points, the number of ordinary double points stays constant. And that means the locus of ordinary double points over my parameter space is a tall extension. And that means whenever I construct quadratic forms from this, nothing's happening. So it varies in a smooth fashion. That's the idea. So the easy lemma says that there is a section, call it well D, H0 on in the sheaf of Grothendieck-Witt rings, such that when I evaluate this section at any y, this is equal to this quadratic Welschinger invariant. So great, but the problem is that this subset is very hard to understand. I mean, it's some, you know, these conditions are not easy to figure out in any practical sense. And the nice thing about this sheaf is if you have a family over A1 in this sheaf, it has to be constant. So it means that this form will be constant on A1 connected components of this scheme, but that's a complete mystery. There's no way to understand what that is in any reasonable way. So the whole brunt of the proof, which actually is exactly what Welschinger does, is to show that my section over here extends to here.
Sorry, I didn't
Yeah.
understand the argument for A1 invariant. What's the argument?
It's just because the global sections over A1 of the sheaf are constant. You have it's a homotopy invariant sheaf. I mean, this is a theorem of Morel's, so
Yeah, okay.
I mean, you have to prove something. But yeah, it's an A1 invariant sheaf. Okay, so the main theorem, so here's the theorem that this LD extends to a global section. At least I got to state the theorem. I can say a little bit about the proof of the sheaf Grothendieck-Witt rings over this whole gadget here. Okay. And it certainly doesn't extend to the whole symmetric power. It's easy to write down examples. When the points come together, all hell breaks loose with this invariant. Doesn't remain constant there. But so, and the corollary is that if we take 2 points, a prime in over any extension field, let's say here, where I can calculate geometrically, so these are 2 points in general, 2 base conditions in general position, which are, so over some field K, or over some field F, containing K. Probably can't see this too well. Maybe I'll write it here. Take two base conditions where everything is nice and geometrically defined. So lying in the same A1 connected component of this larger guy, then the Welschinger invariant for A is equal to the Welschinger invariant for A prime. And it's not, as I said, it's in this guy here, it's easy to show that over the reals, the A1 connected components are just given by the real type, as I mentioned. This implies that Welschinger's theorem. Result by taking the signature. Okay, so the remaining 1 minute, maybe I'll just say a word about how you might go about proving this. So you have something here, and you want to extend it to here. So this sheaf GW is what's called an unramified sheaf, which means if you're on a smooth variety and you have some open subset and a section of GW over the open subset, if you want to see if it extends to the whole variety, you only have to look at the divisors, the codimension 1 subvarieties in the complement of your open subset in the whole variety. And you only need to look at the generic points of each of those divisors. So if your section extends over the generic points of each codimension 1 subvariety in the complement of this in here, then it extends to all of here. So in Welschinger's proof is very topological. What he does, it's more or less the same situation. He says, well, I want to connect 2 points in this smaller subset. I connect them by a real path in general position. So a real path in general position means where the thing is not well defined, I can assume that it intersects as nicely as possible. In other words, it only intersects these bad loci at a generic point. And so what are the bad loci, the complements here? Let me just say what the complements. There are 4 types. There's a cusp, there's a tack node, there's a triple point, and there's something with 2 components. So remember, the things in here give me all the curves lying above are irreducible and have only ordinary double points. This means that one of those curves will have all ordinary double points but 1 cusp. This is where y squared equals x cubed, so you avoid characteristic 2 and 3. So you have, instead of having a curve that looks like this, it has 1 cusp and then the rest ordinary double points. It turns out that this, well, that's supposed to be an ordinary double point. Better? Okay, good. So it turns out that this map, this is the only case, this map here is unramified at each point for which the map into P2 from my curve is unramified. And this is a point of ramification of the map of the smooth curve to P2. So it means that along this locus, this map is ramified. So that's the hardest one to deal with. The tack node looks like y squared equals x to the 4th, something like this. Right, that's a tack node. It's unramified because even though the 2 tangent directions happen to agree at 2 different points, individually it's just a unramified map. So that's fine. A triple point, well, it looks like this, right? That's a triple point. And 2 components just means my curve has 2 components and then, only ordinary double points. So in fact, what you have to do is you have to look at the local deformation theory of these things. Since this map here is étal at these three places, you only need to see that my quadratic form upstairs before taking the trace extends across these three types of special curves. And that's not difficult to do by just making a local calculation. The tricky one is here, and in fact it doesn't extend here. There's a singularity, but since it's ramification of the sheaf, and ramification eats ramification is the buzzword. Since the sheaf is ramified here, but the map is also ramified, things cancel out, and they extend across this cuspidal locus here. So that's the, in a nutshell, how that works. Okay, well, thanks very much.
Questions?
What about the complement of the knot inside the folds in 3D minus 1?
This part here? I don't think there's any reason to think that it would extend there.
What does it look like? Is there any hope for a crossing formula for what happens?
Oh, yeah, I guess. I mean, well, the problem is that this is exactly the smooth locus of this thing. So I don't know how you deal with that. I mean, right? I mean, anytime you have 2 points coming together on something that's not a curve, it's bigger dimension, you get a singularity in the symmetric power. So, I mean, you could try for, you could imagine a crossing formula. I tried doing this. I mean, if you just take the simplest case of pencil of conics, and you take, so it means 4 points. You take 2 of the points and leave them alone, and 2 of the points, let's say, defined over a quadratic extension, so plus or minus square root of t, and you go through t equals 0, you see that 2 singularities kind of come together and cancel out. So you do get, I mean, it really does change, the local mass changes there. But I didn't think of trying to characterize exactly how it changes, but certainly it would be interesting to do that.
Do you have an example where recording the residue fields of all the points in the symmetric power does not determine the A1 connected component?
No. I don't know. I mean, I do know that if you take the general thing I can prove is if you take a base field, you look at points defined over their base field where the actual closed points involved in the 0 cycle have extensions of either rational or degree 2. If you look at that restricted case, then it's only the field type. It's not the degrees, but the actual fields that are A1 invariant. So in that case where the degree of the field extension is at most 2, then that's exactly the invariant that tells you the A1 connected component. And in degree 3, I don't know that, but you can still show by a little trick the fact that the Grothendieck-Witt ring is injective under odd degree extensions. You can show that the field type determines the form. Right. So they may not be in the same A1 connected component, but this invariant is the same on things with the same field type if the degree is at most 3. But I don't know that they're in the same A1 connected component. It's just a silly, simple geometric argument which I can't get to work, and so it's quite naive, the method I use. So it's very possible that you could just be the field type of the 0 cycle determines the A1 connected component, but I don't know.
Okay, I think we'll save further discussion for later. So let's thank Marc again.